In this video, we're going to talk about differentiability. A function is considered to be differentiable at x equals a if we can find the derivative at x equals a. That means the derivative exists. If a function is differentiable at x equals a, it's also going to be continuous there too. So a big concept here is that differentiability implies continuity. However, continuity does not imply differentiability. So if a function is differentiable at a point, it must also be continuous there, but the reverse does not necessarily work. Just because it's continuous does not mean it's differentiable, and we'll look at an example of that in a little bit. First, let's look at f of x equals x squared plus 6x plus 5. It is always differentiable and therefore always continuous. We know that a derivative is the slope of the line tangent to the curve at x equals a. At any x value on f of x, we can draw a tangent line and find its slope to determine the derivative. So what that really means is if I draw in some random tangent lines here just as examples, I can find the slope of these lines, and therefore I can calculate the derivative. And these are just some examples of tangent lines there. Formally, we can say that for a function to be differentiable at x equals a, that basically the limit of the left-hand derivative is equal to the limit of the right-hand derivative, and that is just equal to L, which is our limit. Okay, in this case, the limit cannot be positive or negative infinity. It's got to basically be a finite value. So let's examine some cases where a function is not differentiable at x equals a. There are 4 possible cases where a function is not differentiable or where a derivative fails to exist. The first is at a corner. Here's an example of that limit definition. It is a bit formal, but basically if I look here, the derivative of this whole part of absolute value is -1. The derivative here is always +1. So since the left-hand derivative is always -1 and the right-hand derivative is always +1, these are never going to be equal to one another. So we say the derivative doesn't exist. And that means it doesn't exist at x equals 0. Okay, at let's say x equals 6 here, sure, we can find the derivative is 1, but we just can't find it at that corner. Okay, similarly, we cannot find a derivative at a cusp. Okay, it's similar here to the graph of absolute value, except it's more curved. We don't have the linear pieces. We can't find the derivative when there's a vertical tangent line, okay, because the slope of that tangent line would be undefined. And we can't find a derivative at a discontinuity, and this goes back to the limit definition as well. But basically in this graph here, like at 2, because we have a jump discontinuity, we could not find the derivative there. All right, let's answer some questions on differentiability. Number 1, for what value or values of x is f of x equals 1 over x plus 3 not going to be differentiable? And we're going to identify the reasons. Well, this graph definitely has a discontinuity, and I can tell that because at x equals -3, we would have a vertical asymptote. So I'm going to say it's not differentiable at x equals -3. Because there is a vertical asymptote. That's again when the denominator would equal 0 here. And that's basically a type of discontinuity. Number 2. Is f of x equals the absolute value of x minus 2 continuous and or differentiable at x equals 2? Let's say I graphed this really quick here and I drew a set of axes. Absolute value of x is one, I'll make that a little better here, is one where the point, the corner, is at the origin. But if I am going to do -2 in here, right, I have the absolute value of x minus 2. That's basically shifting it right 2 units. So imagine it looking like this on my graph, okay, and this is at 2. And there we can see there's the corner at 2, so it is not differentiable. However, it is continuous. I could draw that graph without lifting my pen. So I'm going to say at x equals 2, it is continuous, but not differentiable. Number 3, it says circle all graphs that are differentiable at x equals 3. All right, I'm going to zoom in on these pictures so you can see them better. We'll look at 2 at a time. In graph A at 3, I have a discontinuity, so it is definitely not differentiable. For B at 3, we have no problem here. It's just part of the linear portion of the absolute value. So it is differentiable, so I'm going to circle B. At C, at 3, I can't see this on the graph, but I can see that it's going upward and upward and upward. So this is, in fact, differentiable. This is our graph of x cubed here at 3. And then let's look at D. Okay, so if you got a little confused on part B and you said, wait, I thought the corner meant that it was not differentiable. That is only at the corner. For B, the corner is occurring at -1. Notice the difference here on D. The corner is occurring at 3, so this is not differentiable. So I am only in this problem circling B and C. All right, for our last question, number 4, given the piecewise function f of x equals x minus 2, where x is less than or equal to 2, and 2x squared plus 1, when x is greater than 2, which is true? So we want to know, basically, if you look at your answer choices, at 2, is it continuous, differentiable, what combination of these two things? Well, the continuity part we have learned in a previous unit. So let's examine the continuity first. When a piecewise function is continuous at a value, the value where the domain breaks, so in this case at 2, we can set the two pieces equal to one another, substitute in the 2 value, or the x value, in this case 2, and see if both sides are equal. Here, I'm going to get 0 equals 9. That's not true, so I know that it is not continuous. Since it's not continuous here, we know that it is going to be not differentiable, because if we have a discontinuity, it's not differentiable. But here's how we could also show that. Okay, so the way that we can do this is pretty similar, but we're going to do it by using derivatives here. So the derivative of x minus 2 is 1, okay, because that's a line and we have the slope of it as 1. To find the derivative of 2x squared plus 1, we could use the limit definition of the derivative, which is the limit of the difference quotient. Or if you have already learned power rule, you could do the power rule. In either case, you're going to get 4x. And if I plug in 2 here, I'm going to get 1 equals 8, which is not true. So just therefore verifying even further here that this is not differentiable. So our answer is going to be choice D. F of x is neither continuous or differentiable at x equals 2.